Nomenclatures of aldehydes, ketones. Aldehyde. Of course, this is your functional group. Condensed down to the CHO, that's your kind of condensed for the aldehyde group, yeah. Ketones. We can have symmetrical ketones where both R groups are the same, or non-symmetrical where the R groups are different. Of course, aldehydes only have one R group on the carbonyl. Of course, this is called carbonylrite, not a functional group. It's just a component of different functional groups. Amides contain a carbonyl. The carbonyl with an H is called a formyl group. For example, if you take this here and what's the name of that compound?
Formic acid.
Well, with the OH, it's now a carboxylic acid. That's formic acid. Okay. You might want to call it methanoic acid, but nobody calls it methanoic acid. Formic acid. I don't know if I told you, but if you take a lot of ants, put them in your round bottom and heat it up, and formic acid will distill over. Ants contain a lot of formic acid. Whenever they bite you, they put a little formic acid in you and it stings. Of course, the methyl carbonyl is called an acetyl. Of course, if this was an OH, it'd be acetic acid. If it was a chlorine, it'd be acetyl chloride. So these examples I'm giving you are not aldehydes, ketones. But if this was an R group, it'd be sort of like a formyl. These are really just sort of portion names. Okay, you know benzaldehyde, you know acetone, you wash your glass with acetone. Acetophenone, that was on the list when we did aromatics, right? So these are all ketones, aldehydes. Okay, nomenclature of aldehydes. Longest continuous chain. The carbonyl is going to be the one position by default. 1, 2, 3, 4. Butane, remove the E, replace it with al. It becomes butanal. It's an aldehyde, so you're naming it as an aldehyde. Replace the E with al. If it was an alcohol, we would replace the E with OL. Like butanol. This is butanal. You may remember this song by, who was it, Paul Simon? You Can Call Me Al. Nobody knows that song, right? Chevy Chase was in the video. Nobody even knows who that is.
I know.
How does it go? How does it go?
Huh?
Can you sing it?
You Can Call Me Al. Okay. Yeah. Okay, name here, longest continuous chain. Carbonyl is one position, you might as well call that 1. Carbonyl has to be involved in the longest continuous chain. 1, 2, 3, 4, no. 1, 2, 3, 4, 5, 6, yes. Notice you got 1, 2, 3, 4, 5, 6, 7. But carbonyl is not involved in that chain, so forget about it. 1, 2, 3, 4, 5, 6. Hexane, hexanal, what's on the hexanal? 2-ethyl hexanal. Ketones. Replace the E with -one. One. 1, 2, 3, 4, 5. Here, with aldehydes, aldehydes is a terminal functional group. That is, the carbonyl is at the end, at the 1 position. Ketone is not a terminal functional group. The 1 position is not here. The 1 position is the carbon nearest the carbonyl. 1 position is here. Carbonyl gets lowest, but it's not a terminal functional group. Not the ketone. We have it's a ketone, so we're replacing the E with -one. Pentanone. But if that's pentanone, what is this?
3 pentanone.
It's also pentanone. We need to denote where the carbonyl is. Carbonyl is at the 2 position. So this is 2 pentanone. That's 2 pentanone, and what is this?
3 pentanone.
This is 3 pentanone. What if the carbonyl is here? 4 pentanone.
2 pentanone. 2
No.
pentanone.
Carbonyl was there, it'd be the same as that, just turned around, it'd be 2 pentanone. There's no such thing as 4 pentanone. What about 1 pentanone? Can you have 1 pentanone?
Just
Because it wouldn't be a ketone.
It'd be an aldehyde. So there's no such thing as 1 pentanone or 4 pentanone. Or 5 pentanone. But you do have 2 pentanone and 3 pentanone, and these are, of course, isomers. What type of isomers?
Constitution.
The plain kind, constitutional isomers, right? But not steroid isomers, or not. Okay. Examples. What do we have here? Does this look right? Longest continuous chain. 1, 2, 3, 4, 5, 6, 7. Heptanone. Carbonyl's at the 3 position. What else is on the heptanone? 2-methyl-3-heptanone. You can have cyclic ketones. This guy here is a cyclic ketone. The carbonyl carbon is part of the ring. If we just forget about it being a ketone, it's cyclohexane. Cyclohexane. Remove the E, replace it with -one because it's a ketone, it becomes cyclohexanone. The 1 position by default is the carbonyl. You do not have to put it there. By default, it's there. Thus, if you have this compound here, let's put that there and let's put this here. What's the name of this compound?
4 bromo, 5 chloro.
well, 4 bromo 3 chloro.
4 bromo, 3 chloro, cyclohexanone. You don't need the 1. You might say, well, shouldn't substituents get the lowest numbers? Shouldn't it be like 1, 2, 4? No. Carbonyl is 1 position. From there, we give subs lowest numbers. Question?
What if you have like an acid on that?
Like where? Like over here?
Yeah, like a azelaic acid, I guess.
Well, then it becomes a little bit too complex for us.
I mean, would you prefer the acid or like?
How are you going to name that?
I don't know, like something benzoic acid.
It's going to become pretty complex. You can check out the IUPAC book. It's about that thick.
Oh.
We're really pretty much doing the first 2 or 3 pages.
Solid.
Questions about nomenclature? Okay, with test 4, we'll be back to a comprehensive spec problem. Here's a review of NMR of aldehydes ketones. Should largely be a review. You're welcome. Aspect of aldehydes ketones, largely a review. Again, you're welcome for giving you that review summary. The remainder is a lot of miscellaneous things we'll be referring to as we go along. Please be looking at it ahead. Lots of applications of aldehydes ketones. Lots of applications, including when you move to biochemistry. Lots of aldehyde ketone chemistry and biochemistry. Aldehyde ketone warm-up. Okay. I think we can look at the yellow page. We have reactions on the front. We introduced those Last week, things like imines and enamines. Okay. Reactions. We can first classify, look at the difference between non-reversible and reversible reactions. Majority of the reactions we'll be looking at will be reversible. But let's first make sure we know the difference. What are non-reversible? This is when nucleophile cannot act as a leaving group. Those are examples. This is nothing new. Examples may be a hydride or all these anions like from Grignard reagents, etc. If we take maybe like methyl magnesium bromide, right, which is a methyl anion equivalent. We get nucleophilic addition. So the methyl was the nucleophile. We get to this point, right? Can this go backwards?
Nope.
Can this come back down and kick the methyl off?
No.
No. We said we're never going to kick off like a plain H or plain carbon, like a methyl, ethyl propyl, etc. So this cannot reverse. That's why we call it what?
Non-reversible.
Non-reversible. All you can do is throw in some water or some type of proton source, acid, water, put a proton on. Work up, there you go, there's your product. It's actually alcohol. We've done a variety of non-reversible reactions. But here's one we did right here, illustrating the methyl magnesium iodide of bromide. Same thing. Non-reversible. Okay. So the nucleophile cannot act as a leaving group. It cannot turn around and leave. Reversible. Well, this is where the nucleophile can act as a leaving group. It can add, but then it can get kicked back off. This will be any atom that is more electronegative than carbon. We've said before, if you've ever seen it as a minus, it can leave in carbonyl chemistry. Sometimes even carbon will leave, but it will be stabilized somehow. It won't be a plain carbon like a methyl. We will see a couple of examples, such as a haloform reaction or cyanide. This is where nucleophile adds. Okay, electrons up, we get to this point. What we're saying is this could come back down. It's not going to kick off an H or a plain carbon, but we're saying it could kick off the nucleophile. That would just bring you back this way. It would reverse. Some nucleophiles can turn around and leave. But if you go back here, it's really no reaction because you haven't done anything to your starting material. We'll have to look at that. It is possible. We can go forward though. We can put on a proton, work up some type of proton source. We could get this. We're not saying we couldn't get this. This is very similar to above, right? But down here we're going to see further chemistry. That is, we could actually lose this OH group and we can make an additional bond between the nucleophilic atom and the carbon. We can make a double bond here and lose the OH. And we'll see reactions like this. Now, a lot of times this will be acid catalyzed because how do you make OH a better leaving group? Protonated. Okay? But it doesn't have to be. Because if this has a lone pair, we can easily kick that off. Because anytime you have to make a pi bond with a lone pair, you can kick off the leaving group pretty easily. Okay. Now, when we start doing this here, we'll get products that look very odd. But if you follow your mechanism, you'll see that this is where you go. This is where the path leads to. the products will look odd. That's why if you're relying on memorization, it's going to become even more difficult. Please think mechanistically. Someone asks you the product, say, give me a minute, let me work the mechanism out, and boom, here's your product. No, I couldn't just pull it out of the air, but I know how to arrive at the chemistry that's going to take place.
So on this, the first step is shown as reversible, but would the other 2 steps also be reversible?
Yes, actually, this all can be reversible. We'll see reactions where we go from here all the way to the carbonyl compound. Yeah, this can all be, everyone can be reversible. Because of that, we'll talk sometimes about equilibrium, which side is favored, how to push it to one side or the other. Okay, that's a general overview. Okay, reactions. We'll start with simple additions. Then we'll move on to a letter B, which will probably be, I don't know, not so simple.
Complex addition.
No, it's just... Simple addition, though, refers to the carbonyl oxygen is not lost as water. We're not going to lose that oxygen yet. Remember up there we said we can lose it as water? I'm going to call that's going to be B, more complex. Okay. First reaction. Reaction of an aldehyde or ketone with water. First off, I'm showing a ketone. Just about any reaction we do now, it's aldehydes or ketones. I can show either here. I'm just choosing to show a ketone. We can react this with water. We will get this structure here. It's called a hydrate because we've just added water. Hydrate. It's also known as a gem-diol because it's a diol and they're both on the same carbon. They're like twins, Gemini. Gem-diol. Do it? Okay. Mechanism. Hopefully you could all pretty much show the mechanism. I mean, what do we got here? We got a nucleophile, right? We have a carbonyl. Okay, we're going to protonate the carbonyl first.
Oh, yeah, great. No, this is high carbon.
We don't have a strong acid, so we're not protonating anything. You're only protonating when you have a strong acid. We just are adding here. Okay, what does that give? Boom, 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 electrons up. We give that there, right? Nucleophilic addition of water to carbonyl. How do we get final product? H plus transfer. That looks like H3O plus. That looks like an acid at this point. That looks like hydroxide. Guess what? That's going to want to take a proton. It'll take it from that, leave the electrons behind. That's a proton transfer. There you go. All it is water adding to carbonyl, proton transfer, and you have your hydrate. Now this reaction can be catalyzed by acid or base. It may not react quickly with water. If you were going to catalyze this by acid, that is, if you were going to say, we've got an H plus here as well, what would you do first? You would protonate. Then you would add water, and you would get this with an H here, but then you'd have to lose an H. Well, whatever gave up the H plus would take it back. And you'd reform catalyst. Now, hydrates are not stable, usually. You're never going to go to the lab and say, hey, let's make a hydrate of acetone. Here it is, here's my hydrate. You're not going to do that, they're not stable. Okay, here's your equilibrium. All right, this is highly favored. I could have done it like this. Okay, highly favored. such a structure is you got to be leery about it being stable, because if you can form a carbonyl, the carbonyl would be your favorite bonding arrangement. That is, look at here. These electrons could come down, kick that off. We get to this, plus what? Then this can take the H, leave that behind, and there you go. You get your carbonyl plus water. This is favored because the carbonyl bonding is so strong. Also, when you go from here to here, you go from one molecule to two. So it's also favored by entropy. Thus, hydrates are usually just something that maybe occurs in a mechanism or is just a theoretical structure. Okay. There are cases when hydrates can be stable. First off, you need to be able to recognize a hydrate. Is that a hydrate? First off, when we refer to hydrate, we're typically referring to the hydrate of a carbonyl. I mean, you could theoretically add water to anything and call it a hydrate. We're talking about carbonyl hydrates. That is. Because also gymdiol, okay? Can you show, if that hydrate lost water, what would it form? Can you show that?
Carbonyl.
Show the, if that hydrate lost water, if it became dehydrated, what would the structure be?
Like a formal with a chloro.
It'd be that aldehyde there. There is an H on this carbon, right? I just like to draw it in when I do aldehydes. Okay? With this aldehyde, the hydrate is actually the favored form. Now there are others as well. Why would this aldehyde prefer to exist as the hydrate if water's around? And when most other aldehyde ketones prefer to exist in this form.
Yeah, there's three really electronegative
Ah,
chlorines,
okay.
and they're making that central carbon a really strong partial positive, so it's encouraging the reaction.
Encouraging the reaction. But hold on. Are you saying that this is favored because it doesn't react?
No, the three chlorines are making the partial positive really, really partial positive.
Uh-huh.
And as a result, the nucleophile is going to come in like pretty much everything we did last time, and it's going to want to attack.
Yeah, but you're really, that's not really assessing the equilibrium though.
So
For example, I can make this carbonyl more reactive by protonating it with an acid catalyst. But we know that acid catalysts don't affect the equilibrium. So I can make this carbonyl more reactive. That's not going to change the equilibrium. You see what I'm saying?
If you look at the hybridization, that one's
Ah.
sp3, right? So it's not gonna be as tightly held than sp2 with the carbonyl coming out.
This is sp2. The hydrate, the carbonyl is what? sp3. You recognize the difference in the hybridization? So apparently, if we focus in on this, it prefers to be sp3. Why?
It's not as tightly held, the orbitals, compared to like sp2 with the p orbital coming out.
I think that's just a definition of what sp3 means. The chlorines are very greedy, right? They're very greedy. They like to take all your money. The chlorines are going to be able to take more electrons, more money from which carbon? That carbon or this carbon? This one. sp2, the electrons are held tighter. The chlorine can't pull the electrons as much. With this being sp3, the chlorine gets to pull the electrons more. Does that affect anything? Apparently it does. That's my argument. We know that this is favored. That's my argument. Does anybody have a better argument? Difference in hybridization, you get more of the electrons being polarized. That's apparently a good thing. By the way, this is called chloral. That's a common name, Al ending, aldehyde. Chloral. It's called chloral hydrate. Chloral hydrate. Anybody know what that is used for? Or in any old movies, gangster movies?
Chloroform.
Well, it's kind of similar.
No.
It's close to chloroform. Chloroform could possibly be used to make that. Or knockout drops. Finn Mickey, old movies, they slip them a Finn Mickey knockout drop. Chloral hydrate's a hypnotic. Okay, so this is a case where the hydrate is actually stable. Otherwise, you can't isolate hydrates. Where have we seen hydrates before? Oxidation of an aldehyde to a carboxylic acid. The aldehyde is first converted to the hydrate, presence of water. Then when you remove the two H's and put in the double bond OH, then you oxidize the hydrate. Remember that? I briefly mentioned this. I said we'll see hydrates later, we'll analyze later. If you don't want this to take place, if you keep it dry, you can't further oxidize. And that's why we use PCC, because PCC can be used under dry conditions. PCC will oxidize the primary alcohol to the aldehyde, but it won't go further because there's no water present. If there's no water, you can't form the hydrate. If you can't form the hydrate, you can't further oxidize to the acid. So that's where we saw hydrates before. Now note, the equilibrium here favors this, right? That doesn't mean some is here. And when this is oxidized, what happens to this equilibrium? When this is removed, it keeps shifting. So even though at one time this is favored, the minor component gets continued on, and it all goes. Okay? Next reaction. Reaction with HCN. We're going to form what's called a cyanohydrin. CNOH, both on the same carbon, a cyanohydrin. This mechanism can be done two different ways, depending on how acidic this is. If we consider this an acid, it's a weak acid. We can consider it ionized. Is this strong enough to protonate? We could do it like this. We could protonate our carbonyl with the HCN. We got the nitrile. This is a cyanide. How do you get final product? By the way, let's put the charge on this end because it's the carbon that's charged. This adds here, electrons up, and that gives you your cyanohydrin, right? Just a simple addition to the carbonyl. We did protonate. You could do this the other way. You could bring in cyanide first, electrons up to give an O minus, and then the O minus could take the H, and you could get there that way. It all depends on how acidic, if the carbonyl is being protonated first or not. How acidic is HCN? It's not a strong acid, but it may be acidic enough to protonate first. Either way works. I showed it this way. Basically, what do you need here? You need a cyanide source, and you need a proton source. They can both come from HCN. By the way, remember in organic 1 we made halohydrins? Now actually, if that's a halogen, that is a halohydrin, but that's more of a geminal. You remember in organic 1 we made well, alkene, chlorine, and water? Final exam, which is comprehensive, right? Product of that reaction right there.
Bold CO.
It's bisphenol too.
Right? What's an enantiomer? What was that called? Halohydrin?
Yeah, bisphenol.
Yeah. Halohydrin. It's like this came from some water there somehow. Now this is where the halogen and the OH are on the same carbon, so it's not like the halohydrin is exactly we made in organic 1. But with the cyano-OH, it's called a cyanohydrin. Okay, cyanohydrins can be isolated, usually. You can go to the lab and make a cyanohydrin. Although, can it go backwards? Could you envision the cyanohydrin coming back to this?
In a basic condition, probably.
By the way, what letter are we under?
We're still under A. Still under A. I mean, all you gotta do is.
Are we under Roman numeral 1 or 2?
So it can go back.
Reverse it. Yeah, it can come back.
Are we under Roman numeral 1 or 2?
2.
2. And Roman numeral 2 says what?
Reversible.
Yes. Yes. We're under Roman numeral 2. Everything is reversible that we're looking at. That is, the cyanohydrin can go back to the carbonyl compound, and if it did, it would make that plus what? ACN. Now I say heat or time or biological enzymes. Basically, cyanohydrins are very toxic because if you ingest them, the reaction can reverse and you generate ACN. And what do we know about that?
Yeah.
It's very deadly. Okay, cyanide. So if it reverses, you're going to produce cyanide. A number of years ago, cattle somewhere in Africa were just dropping dead in the fields, dead cows. What was going on? It turns out that the hay or the grass that they were feeding on somehow got infected with a organism, a microbe, a bacteria or something, that produced a cyanohydrin. Bacteria was producing this. Cow was eating the hay, eating this. This was getting in the body. It was reversing and generating ACN, and cows were dropping dead. Okay? Bacteria can produce compounds. I mean, they produce penicillin, right? Question?
Yeah, for the halohydrin, if you have a regular halohydrin, we said that if you use Na or NaOH, we can form epoxide, right? So would it form in this like gem halohydrin in this case?
Well, actually, this gem halohydrin is not going to be stable.
Okay, so it's gonna.
It's going to lose HX. Because these electrons can come in here and kick off like the halogen, right? Get that, plus X minus. And then this can take the H, and you get the carbonyl. That's going to be the driving force.
Okay.
Because like we said, the carbonyl is a very strong bonding arrangement. So very often when you have two leaving group, or like something like this on the same carbon, carbonyl is going to be favored. Like if this was an OH-OH, which is a hydrate. This is going to lose water by the same mechanism. Somehow it's going to kick one off and the other, it's going to come back and take the H. Okay? Same thing here. How can this go backwards? These electrons come in here and kick off the cyanide. What does that give? It gives this. I mean, we're going exactly backwards, right? If this came in and kicked off the cyanide, we would get these two. Then the cyanide could take the H, and you would get back these. But that's a very key point. The carbonyl is typically a favored product. Now, but I did tell you, cyanohydrins can be isolated, but they're very fragile. You have to be very nice to them, or they will decompose and revert back to this. This will decompose, it will break apart, and go back to this. Heat or time, you know, it'll give enough time, it'll kick this off, and it'll or biological enzymes, which to make they do magic. Question?
Could you use hydroxide to reverse it?
And possibly you could envision kind of deprotonating it.
It forms a double bond.
Yeah, there's
another
lots of
hydroxide
mechanisms.
comes.
The more you know, the more you can do. Can reverse. But again, unlike hydrates, which you're never going to really isolate except for unique cases, you can isolate these. You just got to be careful. They'll reverse on you. The pit of like stone fruits, peaches and apricots and stuff, those pits contain cyanohydrins. They're in the form of like glycosides. But that's why you don't want to eat the pit of a peach or something. No, who would want to eat that anyway? But you got to be careful. You know, you'll ingest cyanohydrin and it'll decompose to the ACN. Okay, cyanohydrins. If we were going to make a cyanohydrin today in lab, we'd have to pull out a tank of HCN. It's a gas. The problem is if you have an HCN, a gas, and it's going to chase you around the lab. And some of you guys don't know how to put caps on bottles and stuff. And I'm afraid you'd leave the tank open, and HCN would be spewing out, and we'd all be dead. Okay? In the end, HCN is not that convenient. Can we use alternative reagents? Yes. What do we need to do this reaction? We need cyanide and we need a proton source. It doesn't have to come from HCN. It can come from these reagents. Here. Cyanohydrin. This is K plus, cyanide minus. There's your cyanide. What is this? Sodium bisulfate. H2SO4 we commonly use. But what about HSO4 minus, which this is here? This is also acidic. It's got one acidic proton left. So this is an acid source. So there's your cyanide, and this is your H plus source. Now you can use a variety of H plus sources. Why is this more convenient than using HCN? Both of these are solids. KCN is a solid. It's a salt. This is actually a solid. It's even more convenient than sulfuric acid. You spill this, you're going to have a mess. Spill this, you can sweep it up with a broom. Two solids, which would you rather use? Two solids or a gas?
Two solids.
See, these aren't going to chase you around the room. Safer, more convenient, easier to store. Okay? Understand the chemistry there. We got a cyanide source and we got an H plus source. Do the same mechanism we did up there. Okay, make our cyanohydrin. By the way, if we had a cyanohydrin and we treated this with acid and maybe heat, what type of product could you envision? Any chemistry there?
Like a carboxylic acid or something.
What type of chemistry would you propose? How about that right there?
Yeah.
Hydrolyze the nitrile to the carboxylic acid, with the amide being the intermediate. The amide could be further hydrolyzed. So, you could do chemistry with the nitrile, yeah? You could even do chemistry with the OH at some point. I mean, I can't envision anything with just aqueous acid. You can't dehydrate that alcohol. There's no carbon to make the alkene. Okay? The white handout shows some miscellaneous, including the talks about the cyanide from like peach pit, etc. This is actually the type of compound that's in the peach pit. With these carbohydrates, it's called glycoside. It's a little bit, we're going to have to refer back to this again. It's really in the form of an acetal, which we'll cover soon. The acetal can get hydrolyzed, reversed, and this can generate the cyanohydrin, but then the cyanohydrin can lose HCN and go on. That's ultimately how you can get there. We'll see acetals in a little bit. B. I think this is an acetal. Oh, hold on, we're going to B. What was A? A was simple additions. We saw two simple additions: hydrate, water adding to carbonyl, and ACN adding to carbonyl. And when we did this, did we lose the carbonyl oxygen? No, it remained there as the OH. Starting with B, we're going to lose the carbonyl oxygen as water. So these are not so simple. I don't call them difficult or anything, but they're just not as simple. First reaction is reaction with an alcohol acid catalyst to make an acetal plus water. And if we star that oxygen there, that oxygen was originally this oxygen. We're going to lose the carbonyl oxygen as water. What is an acetal? You need to know that. It says, first off, if under my hand was H's instead of ethyls, what would that be?
Hydrate.
It'd be a hydrate. An acetal is OR instead of OH. It can be ethyl, methyl, whatever. Alkyl groups. Two ORs is an acetal. Two OHs is a hydrate on the same carbon. We'll see variations of this a little bit. Call it acetal. Okay, mechanism for this. Like many of the mechanisms we're going to see, I would hope that you would be able to do like 80% of this on your own, if not all of it on your own already. It's the same general ideas. Okay? We do have an acid catalyst. What do you want to do first?
Protonate the OA.
Protonate carbonyl. I'm going to do it without actually showing the mechanism. We can all protonate carbonyls. Anytime you're doing carbonyl chemistry with acid catalyst, protonate carbonyl first. Now what? Now we have the ethanol. Adds, electrons up. Boom, boom, boom. Electrons up, that becomes OH. We have a methyl, and we have O. I'll draw that as an ethyl. We did not lose the H, plus charge.
Proton transfer.
Proton transfer.
We just made that bond there. Ethanol added, electrons up.
Proton
Proton transfer in the word.
Proton transfer, yes. We know we're going to lose this oxygen.
No, we don't. We're going to lose it.
Okay. H plus transfer. Why does the proton get to sit on that oxygen? Why not sit on this one? Leave the lone pair behind. Just we're only transferring the H plus, H nucleus, to one of those lone pairs. Lone pair left behind. We get to this structure here. What next? We have a lone pair here. Anytime you have a lone pair, make pi bond, kick off leaving group. What does that give? Boom, boom, boom. I'm going to draw this methyl kind of up. Now we have a double bond to that oxygen, and it has an ethyl on it, one lone pair left, a plus charge. Double bond to oxygen, but there's an ethyl on it.
Now you're okay.
Now I gave you a big hint here, two equivalents. Hopefully you see that here.
Do the same thing.
So now.
This is like a carbonyl that's protonated. It's got a positive charge. Not with an H, but with an ethyl. We now have another ethanol. I mean, what else could happen here? This is not going to be an end product with that positive oxygen. What can happen here?
Bond to that carbon,
Come
kick
around,
electrons
grab the
up.
bond, keep the electrons back with that.
Water could add, and we can come back this way.
Oh, yeah.
But instead of water adding, how about ethanol adding? Boom, boom, boom. I'm
Methyl
going to draw the ethyl down. There's the bond we just made. Hold on. It's like ethanol adding to a carbonyl, electrons up to the oxygen. And that has an ethyl. So we just brought that in, electrons up to the oxygen. How close are we to our product?
Just catalyst.
You gotta lose the H.
You just got to lose the H. Well, what gave it up?
Water.
What's your favorite acid catalyst?
HCl.
Maybe we use HCl. Then Cl minus. Take the H, leave that behind, and we get that plus HCl catalyst reformed. We made acetal. What did we liberate? We lost water. Let's make a few final comments about this. This is a true equilibrium reaction. We're still on the Roman numeral 2 the rest of the semester. We can reverse. If you have an acetal, can you protonate one of the oxygens of the acetal? Sure, why not? And if you do that, can the other oxygen come in and kick off that ethanol? Sure. And if you do that, could water then come in here instead of ethanol?
Sure.
And could the proton then transfer over to this oxygen?
Sure.
And at this point, could this come in and kick off the ethanol?
Yeah.
You see how it could go backwards? It's a true equilibrium. How do we drive this reaction to the right?
You add a lot of
Remove
extra.
water. Remove water. We'll pick up here on Friday. How do we remove water?